Welcome to the deep dive. If you want a shortcut to understanding how we're winning the modern war on cancer, you really have to look past, the traditional chemotherapy and radiation. You have to focus on our own internal army, the immune system.
It is the ultimate defense. I mean, historically, the very first line of defense is DNA repair, right inside the cell itself. When that fails, the cell becomes abnormal, and that's when the immune system should step in.
Should, but it doesn't always.
Exactly. The problem is cancer cells are masters of disguise. They are smart enough to convince our internal security forces that they're friendly.
And that's really the mission for this deep dive. We're unpacking the revolution in immunotherapy, the strategies designed to teach your body how to, stop being fooled and start fighting back. We're going deep on three core approaches: immune checkpoint inhibitors, or ICIs, which take the brakes off the immune response.
Yeah.
And then the really hyper-targeted cell engineering of CAR-RT and BiTE therapies.
To appreciate the power of these new tools, we should probably do a quick refresh on the soldiers we're arming. Our immunity has two arms. You've got innate immunity, that's the immediate, non-specific, rapid response team, NK cells, neutrophils.
The first responders, the ones who shoot first and ask questions later.
Right. But the real precision force is the adaptive immunity. This system is a bit slower, but it develops specific target recognition, and crucially, it develops memory. The stars of the show today are T cells, specifically the helper T cells, which sort of organize the attack, and the cytotoxic T cells, the CD8 plus killer cells that are designed to physically destroy the tumor.
And those are the cells that cancer learns to shut down.
That is its main strategy: suppress those killer cells.
Okay, so let's unpack that first big breakthrough, immune checkpoint inhibitors, ICIs. I think the reason this concept resonated so deeply with researchers is it finally explained why T cells were, showing up to the fight but just standing idle. Cancer wasn't invisible, it was just throwing up a do not disturb sign.
That stop sign is what we call an immune checkpoint, and these are natural inhibitory pathways. They exist in healthy people to stop the immune system from, overreacting and accidentally attacking your own tissue.
So it's a safety mechanism.
It's a safety mechanism that cancer hijacks to put the T cells to sleep.
So what are the mechanisms being hijacked? Our sources point to two critical checkpoints. Let's start with the big one: PD-1 and its ligand, PDL1.
Okay, so PD-1 stands for Programmed Cell Death Receptor 1. It lives on the surface of your activated T cells.
Right.
When a cancer cell expresses the ligand, that's PDL1 or PDL2, and it binds to the PD-1 on that T cell, it delivers a deactivation signal. It's like the tumor is shaking the T cell's hand and whispering, "Stand down, you're not needed here."
So it turns it off. And the second major brake pedal is CTLA4.
Right, CTLA4, it's another inhibitory receptor, but it acts much, much earlier in the process. It blocks the crucial co-stimulatory signals that are required for the T cell to even get activated and proliferate in the first place.
So PD-1 is silencing an already active T cell, but CTLA4 is stopping it from ever really getting going.
You've got it. It's blocking activation itself.
The principle behind ICIs, then, is actually pretty elegant. It's just systematic blockade. We use a monoclonal antibody to physically block these suppressive signals. We're either blocking the receptor on the T cell or the ligand on the tumor cell, taking off the brakes.
And releasing the native anti-tumor immune response. It's an incredibly widespread approach now. The key drug names you'll hear are the CTLA4 inhibitor, ipilimumab, and then the PD-1 inhibitors like nivolumab and pembrolizumab. Then you have the PD-L1 inhibitors, drugs like abilumab and durvalumab, which target the tumor cell signal instead of the T cell's receptor.
It is striking how broad the use of these PD-1 inhibitors has become. We usually think of cancer drugs as targeting a specific organ, lung, breast, colon. But pembrolizumab has FDA approval for any tumor that exhibits certain characteristics, regardless of where it started. What are those characteristics?
And that's where the real insight is. We're learning that the response isn't just about what the tumor looks like on its surface today. We look for a high tumor mutational burden, or TMB.
Tumor mutational burden.
Right, which basically means the tumor has accumulated a lot of historical DNA damage. It's highly mutated. These damaged tumors are more likely to generate strange proteins, neoantigens, that the immune system can recognize.
Wait a second. So the tumor's history of damage is what makes it vulnerable to treatment. That connects right back to your opening point about DNA repair being the oldest defense.
Absolutely. The failed DNA repair leads to high TMB, which makes the tumor look inherently stranger to the immune system. We found that cancers related to, say, heavy smoking, like lung and bladder cancer, or inherently immunogenic tumors like melanoma, They respond well.
because they have that high TMB.
That and an inflammatory microenvironment. It's not always as simple as just looking at PD-L1 expression on the tumor surface. That's not always the best predictor.
And this is where the listener really needs to pay attention because the side effects of ICIs are completely different from anything we've dealt with before. When we talk about conventional chemo, we worry about, systemic cell killing, hair loss, myelosuppression.
Dangerously low blood counts.
Right. And those things are rare with ICIs.
Yeah, very rare. Instead, we have a whole new category of toxicity, immune-related adverse events, or IREs.
IRAs.
Think of it this way. When you remove that brake pedal, the immune system, which is now highly activated, runs the risk of recognizing healthy, normal tissue as a target. You are essentially trading systemic cell poisoning for a controlled, deliberate autoimmune state.
An induced autoimmune condition that can affect literally any tissue in the body. That is a startling trade-off. What should we be looking for?
It's an alitis of any organ system. The most common are colitis, which is inflammation of the colon, and that results in sometimes very severe watery diarrhea that affects 15 to 25% of patients. We also see pneumonitis, inflammation of the lungs causing cough and shortness of breath, and a lot of endocrinopathies, where the immune system attacks hormone-producing glands, leading to hypothyroidism or hyperpituitarism.
And if you combine therapies, say using a PD-1 inhibitor along with that CTLA-4 inhibitor, ipilimumab, does the severity of those IREs go up?
Significantly, yeah. The CTLA-4 inhibitors, like ipilimumab, they tend to cause higher rates of severe, high-grade toxicities even on their own. Combining the two gives you the most potent anti-tumor effect, but it absolutely elevates both the rate and the severity of these side effects.
It's a delicate balance.
A very delicate balance.
Okay, so we've covered unblocking the native immune system. But what if we need more than the native T cells can deliver? Now we shift gears. Section 2. Adoptive T cell therapies. We're moving from removing the brakes to custom engineering the soldiers themselves.
This is the high-tech, highly personalized approach. We are literally taking the patient's own immune cells, modifying them in a lab, and then injecting them back in with a hyper-specific instruction set.
Let's start with CAR-RT, or chimeric antigen receptor T cell therapy. The poster child for this is the drug tisagenoclusol. Walk us through the logistics, because this sounds like a radical process.
It is. The first step is apheresis. We remove the patient's own T cells. We call them autologous because they belong only to that patient.
Okay.
They are then flown, literally flown, to a specialized manufacturing center. There, they're genetically modified. We insert a new piece of genetic code that causes them to express a chimeric antigen receptor, the CAR.
And that CAR is the custom targeting device.
Exactly. The CAR is engineered to specifically recognize an antigen on the cancer cell like CD19 in leukemia. We then grow millions of these hyper-specific CAR T cells in the lab, basically creating an army of targeted assassins, and then we infuse them back into the patient.
The power here is just incredible. I mean, it often produces remissions in patients who had run out of all other options, especially in certain blood cancers.
Yes. The main indications for tisagenoclusol are highly specific right now. B-cell precursor, acute lymphoblastic leukemia, or AL, especially in children and young adults who have relapsed or failed other therapies. But because these therapies are so powerful, the risks are equally profound.
You mentioned critical toxicities that carry a black box warning. That immediately flags severe danger. What are the primary risks?
The two biggest risks are cytokine release syndrome, CRS, and associated neurological toxicities.
Okay, let's focus on CRS, cytokine release syndrome. If the IRAEs from ICIs are the body becoming autoimmune, what exactly is CRS?
CRS is what happens when those engineered T cells hit their target and immediately start killing millions of cancer cells all at once. When T cells activate, they release signaling proteins called cytokines. They're like chemical alarm bells.
Right.
With CRT, the T cells release these cytokines, especially one called interleukin-6 or IL-6 in massive, uncontrolled quantities.
So it's not the body attacking healthy tissue. It's the body having a full-scale shock-like reaction to the engineered soldiers doing their job too well.
Precisely. It's a systemic inflammatory activation. It leads to rapid symptoms like extremely high fever, dangerously low blood pressure hypotension, and vasodilation. In severe cases, this cytokine storm can lead to acute respiratory failure, or even death.
That sounds like an emergency requiring immediate intervention. How do you shut down that intense inflammatory cascade once it starts?
The treatment is very targeted. Since IL-6 is the primary driver, the key is the early administration of tocilizumab. This is a monoclonal antibody that blocks the IL-6 receptor. It essentially mutes the most dangerous inflammatory alarm bell.
Which brings us to our final engineered strategy. It's one that's a bit less complex logistically than CAR-T, but it achieves a similar goal. BiTE therapy, bispecific T-cell engagers, like the drug blinatumomab.
Think of BiTEs as a bridge builder. So unlike CAR-T, where we have to genetically modify the T cell, BiTEs are engineered antibodies that you can manufacture in bulk and just infuse into the patient. They are bispecific because they have two arms designed to bind two different things at the same time.
Okay, so what are the two targets blinatumomab is trying to link?
One arm has a CD3 binding site, and CD3 is expressed on the patient's existing T cells, the killer cells. The second arm has a CD19 binding site, and CD19 is expressed on the malignant B cells we want to target.
So the antibody is like a molecular handcuff. It forces the patient's existing unmodified T cell right next to the tumor cell.
It connects them so intimately that it forces the T cell to activate and exert its cytotoxic effects, killing the tumor cell. It effectively skips the need for that complex, customized T cell modification.
A sophisticated, off-the-shelf way to engage the immune system.
Exactly.
And blinatumomab is also used for relapsed refractory B-cell precursor OL, just like CAR-T. Do they share similar toxicity profiles then, given the shared mechanism of rapid T-cell engagement?
They absolutely do. BiTEs also carry that black box warning for cytokine release syndrome and neurological toxicities. The severity might be different than with CAR-T, but the risk of an inflammatory storm and CNS involvement is very real and has to be monitored very closely.
We've covered these highly sophisticated modern immunotherapies, but we should probably zoom out for a second to address the fundamental technology that makes all of this possible. Monoclonal antibodies or mAbs?
Monoclonal antibodies are the backbone. They form the structure of the ICIs we discussed. They are the drugs that block PD-1. They also form the structure of the BiTE bridges we just mentioned.
All designed to target a single specific antigen.
Exactly. And outside of blockade or serving as a bridge, the traditional way mAbs kill cancer cells is by acting as highly specific flags. They attach to the cancer cell and mark it for destruction.
How does that work?
Mainly by activating two processes: complement-dependent cytotoxicity, CDC, and antibody-dependent cellular cytotoxicity, ADCC. These processes basically summon other parts of the immune system, like NK cells, to come and destroy the flagged target.
And we see non-ICI mAbs targeting much broader cellular mechanisms too, like trastuzumab, which is a mAb that blocks the HER2 growth receptor in breast cancer, essentially starving the tumor.
Or rituximab, which targets the CD20 receptor in lymphoma to trigger apoptosis or programmed cell death. We've also made huge strides in making these drugs safer over the decades. Earlier mAbs were called murine because they came from mice.
And the human immune system often rejected them.
Severely. We've progressed through chimeric and humanized antibodies to the fully human antibodies we generally use today.
That progression from mouse to fully human is critical because it drastically reduces the risk of the patient having an allergic, sometimes fatal immune reaction to the therapy itself.
Right, but even with fully human antibodies, general side effects persist. You can still see typical flu-like symptoms, chills, fatigue, headache, and there's always a risk of allergic infusion reactions.
And some have very specific risks, right?
They do. For anti-angiogenesis drugs like bevacizumab, which block tumors from growing new blood vessels, a major side effect we watch out for is bleeding risk.
This entire deep dive really illustrates a profound philosophical shift in how we treat this disease. We've moved from the indiscriminate destruction of chemotherapy to highly targeted immune manipulation.
The synthesis is clear. Cancer immunotherapy is all about specific control. We're either removing systemic barriers using ICIs, which results in the unique risk of IREs, that induced autoimmune state, or we are custom engineering soldiers with CAR-T and BiTEs, which results in the unique risk of acute cytokine release syndrome.
The toxicities are severe, but they are highly specific to the underlying immune mechanism.
Yeah, exactly.
And that leads us back to the predictive power of these new tools. If we look again at ICIs, we found that simply measuring PD-L1 expression on the surface of a tumor, well, it wasn't the most accurate predictor of success. Instead, factors like high tumor mutational burden and the inflammatory environment were key.
Which raises a profound question that you should consider for the future of medicine. If we know that a tumor's history, how damaged its DNA is, and its surrounding environment are better indicators of response than its current surface features, how should that change the way we test patients? I mean, what does it mean for testing to pivot away from just surface biomarkers and focus more intensely on the historical DNA damage and the unique ecosystem that the tumor has built around itself? That shift is already redefining oncology research.
A stunning implication for the future of personalized medicine. Thank you for guiding us through this incredibly complex landscape.